Hello everyone. In this video, I am going to cover a moment, skewness and kurtosis, and that too under a probability distribution. So we are going to see, we get an idea about the understanding of different shape characteristic of the distribution like skewness and kurtosis. So let us see what point I'll cover under this discussion. I'll discuss about the moment, about origin, about mean, then their relation between these two moments, and we will discuss about the skewness kurtosis topic, concept, and also I'll cover two examples. One is for the discrete distribution and the second one will be for the continuous. So let us see what do we mean by the moment. Actually, it gives us an information about shape, location, dispersion or asymmetry of the data, or you can say distribution under the probability. And in fact, it is also a quantitative summary, and in it is not only confining to mean and variance, it can go beyond it. Means for a different shape characteristic can be studied with the help of moment. So let's begin with the first very important moment, which is called moment about origin. Now moment about origin is also known as a raw moment. Now what we can do here, first of all, let us see if there is a rth moment about the origin, then how we can denote it. So we are going to denote it by mu r dash. So dash is one important point we are going to use for the raw. And how we will define it, we define in terms of expectation of x to the power r. So we apply expectation to the x to the power r. Now second point comes, then how to crack the expectation. So if let's say I want to find the value of expectation of x to the power r, what I am going to do is either I can deal with the discrete probability distribution or I can deal with the continuous. So if it is a discrete, we are going to multiply x to the power r with its corresponding PDF. If it is a discrete, we'll take a sum. And in case it is a continuous data, we can take x to the power r and multiply with its corresponding probability, and then we can integrate it from minus infinity to plus infinity. So here I used a px notation for the discrete probability and fx notation for the continuous. So these are important point for the evaluation purpose. Since in the discussion of this skewness and kurtosis, we only need a 4 moments. They are also called a key raw moments about that origin. So first moment, second moment, third moment, fourth moment. How do we get it? In the previous formula of mu r dash, we can put r1. We will get it mu1 dash, and it is equals to ex. And you can see that ex is also known as a mean, and we denote it by a notation mu. So it means the first raw moment is nothing but it is giving us a mean of the distribution. And for the second, third and fourth, that is mu2 dash, we will evaluate ex square. If I want to find out the third rth raw moment, then we can find ex cube. And for the fourth raw moment, we will find out ex to the power 4. So these 4 moments we can use depending upon the question. If it is a discrete, we just saw how to open it with the summation, and for the continuous we can do integration. In the last problems we will see how we can implement it. And the next very important moment in this discussion is about a mean, and this is also known as a central moment. Basically moment, we can discuss about any point because we want to see how the function is behaving with respect to the reference. So 0 is sometimes we take a 0 as a reference, sometimes we take a mean as a reference, or sometimes we can take any other value as a reference. But for the time being, we are just confining ourselves to the mean and origin because they are required for the study of skewness and kurtosis. So central moment, how do we write? For example, if I want to write the rth moment of the mean about the mean, so first of all, we should calculate mean if I want to find a central moment. So mean is required, and we can denote it by mu r just to differentiate from the raw and to the central. We use dashes for the raw and just mu r for the central. And the definition is in terms of expectation. So what we can do? We will take data point, or you can say a variable, deviate it from the mean, and then find out the power r and its expectation. So just like we define the expectation, how we can open expectation here, we can see it. If it is a discrete, we will take a sum, then multiply x minus mu to the power r to its corresponding PDF. If it is a continuous, we can integrate from minus infinity to infinity, same x minus mu to the power r with f of x dx. So this is a process if I want to directly apply expectation. So this is a technique to deal with the discrete and the continuous, right? And one point more I want to make clear, that these moments are under pure statistical, where the frequency is given. So formula got little change. When it is a probability, the formula is in terms of PDF. So there is some changes in the formula writing of the mean, and you can say expectation. So we have to be very careful that either we are doing the topic under probability distribution or we are doing under the statistic. Accordingly, the formula can be modified. So currently it's a probability distribution. Now the same manner, we are interested in only the key central moments, which are the first four central moment. So we will see first, second, third and fourth, and we'll also see what they are actually representing. So when I say r is equals to 1, the first central moment, mu 1, and it is e x minus mu to the power 1. So when we open it, ex, and mu being a constant because it's a value, so e of constant is the same constant. So when we observe that ex is also a mean and this is also a mean, so when you are taking a difference, you are getting answer 0. So we observed from here the first central moment is always 0. And what about the second? When we plug in r is equals to 2, so we are getting mu 2 is equals to e of x minus mu whole square. And we know that this is the definition for a variance. We can write it equals to sigma square. So it means the second central moment is nothing but it is defining the variance. And variance is actually talking about the spread of the data set point, right? So the third moment is when we take a power 3, we write mu 3, and mu 3 is also is an indicator for the skewness. Which side data is skewed, that will be described with the help of mu 3. And fourth central moment, mu 4, which is e x minus mu to the power 4, this will describe the kurtosis part, right? So when we will discuss what does it mean, we will see in the later part. And sigma, as you know, under the variance part, it is nothing but the standard deviation, which is a square root of the variance. So these are all symbols which we may come across in our later part of the discussion. So we have to remember it. Now, one of the very important point which we should make sure it should be clear, that there is a relationship between raw and central. Why? Because whenever we are writing mu 2, we are writing e of x minus mu whole square. So we can open it because it is a minus b to the power 2. So we can open and expand and we'll write everything in terms of the raw moment. Because when we write on x square minus 2x mu plus mu square and then we implement expectation and simplify it, we'll see we get this result. So before applying the summation and integration, what we can do, we can open the power mode and apply expectation and then write down everything in terms of the raw moments. So this way the relation can be established, right? This is the formula for the third moment, and this is a formula for the fourth moment. Now let's come to the skewness one. What do we mean by skewness? Skewness is just a tilted graphical presentation of the data, or you can say in a simple way when there is no symmetry, or you can say lack of symmetry. Now there are three situations the distribution can look like. The number one, I will discuss the middle one, which is symmetric and normal distribution. So when you observe that your data is distributed very nicely about a point, 50% of the data on the one side and 50% on the data on the other side. And what are these points? The mean location is the same, median is same, and mode is same. That means when your distribution is symmetric, mean, median, mode are same, right? And when they are not same, either they are left skewed or it is a right skewed. So how do we identify it is a left skewed? So when you observe that there is a long tail on the left side, right? That means this data is in the negatively left skewed, or we can say negatively skewed. So how we can remember long tail on left, left skewed, negative. Same manner, when do you say that data is right skewed? When your data point are skewed in the positive direction, right? So there is a tiltness in the positive, there is a tiltness in the negative side. So you can call it a positively skewed, and you can say that long tail on the right hand side. And you can observe that the mean location is here, which is less than median and mode, because mode is having a maximum probability. So the location will automatically shift, and here mean is bigger than median and mode. So this is also one of the way to identify whether it is a positively skewed and a negatively skewed. But in our current discussion, we are going to use a moment formula. So how we can use it means, what is a measure of skewness using moment? We know that mu3 will give us a clue about the direction. If it is positive, we can say it is a positively skewed. If it is negative, we can say negatively skewed. But if we want to find out what degree and what is a ratio, we can use this formula called a coefficient of skewness, denoted by this gamma 1. And the formula is, we can use this formula by using mu3, mu2 to the power 3 by 2, or alternatively what we can do, because mu2 is a second moment and second moment is a variance. So if I plug in the variance value, I'll get this formula. So it is up to you, whatever is a convenient way to solve, you can use it. So mostly we implement this mu3 upon sigma 3, right? Now next, what are the interpretation part? So if gamma 1 turn up to be 0, we can declare that distribution as a symmetric. If it is greater than 0, we can call it a right skewed, positively skewed. If it is less than 0, it is left skewed. So this is an we can interpret what result can be done via this gamma values, right? Gamma 1 value. So this is a technique to measure skewness. Let's see how we can measure the kurtosis. Now kurtosis means what? Kurtosis is giving us an information about the data peakedness, means what is the shape of the data, whether it is very sharp or whether it is flat. So it is talking about that. So it is talking about a sharpness and flatness of the curve when you are comparing with the normal. That's one important point. So let's say I am considering that the normal distribution is like this, which is not far very narrow tails, or not very long tails. It's perfectly normal, and we can call it a mesokurtic, right? But if the it is very sharp, then we can call it a leptokurtic, and if the data point or spread is a lot, we can call it a platokurtic. So these are the different name also for the sharpness, for the normal, and for the flat. So let's see how we can measure it. When we want to measure the kurtosis, obviously we can use mu4, because mu4 is talking about the kurtosis. It gives us an indicator for that. But for the relative point to compare it, we can use a coefficient of kurtosis, and it is denoted by beta 2. And we can calculate is mu4, which is a fourth central moment with respect to the square of the second moment. So central moment. So we can again here also, the in both the formula, central moment, second central moment is in the denominator, and it is equals to sigma square. So when you plug in, you will get a sigma 4. So you can use this formula also for the convenience. And in the same manner, one more formula is there under the kurtosis, which is called the excess kurtosis. For the normally distribution, the value of beta 2 must be 3. So if you want to compare at what is an excess of kurtosis, whether it is less than 3 or it is more than 3. So what you can do is, for gamma 2, when you delete 3 from beta 2, either we will get a gamma to be 0, so we can declare to be the mesokurtic, and when it is a greater than 3 or this is greater than 0, we can say it is a sharp peaked, so leptokurtic, and when it is less than, or you can say less than 0, it is a platokurtic, means when beta 2 is less than 3 and gamma 2 is less than 0, we can say it is a platokurtic, or we can call it a flatter top. So these kind of observation we can interpret with the help of this kurtosis. So what we can do now, let's take one, before taking an example, let's recall the summary part. Obviously, I'll take one example after that. What we can summarize, that what kind of characteristic of distribution these moments are giving us. So the first raw moment means origin is giving us a mean, and it is talking about what kind of measure it done. It is telling us a location of that point. So it is a central value of the data. And what is the second moment about mean, which is giving us a variance and measure dispersion spread of the data, means how it is away from the mean. And the third moment about the mean is nothing but it is describing the skewness. This tells us about the asymmetry or lack of symmetry. So it means it tells us whether the data is skewed to the left or to the right. And fourth moment about mean is talking about the kurtosis, and what it measure the peakedness and tell us whether it is a peaked or flat as compared to the normal. So this is a summary of whatever we have discussed so far. Now let's take an example. In first example, for the discrete data, I have taken four values data and its corresponding probability, and we are going to find out the first central moment. We will discuss skewness, kurtosis. We are going to take a coefficient of it, right? And then we will discuss what kind of distribution we are facing in this case. So for that, let's take a calculation work. We need for the raw moment, right? So we are going to find out the sum of x into p, which is equals to mu1 dash. We are going to find out mu2 dash, and this is mu3 dash, and this is mu4 dash. So we are interested to find out these values, right? So this will be multiplied with 0. This is 0.1 because x into 0.6 because 2 into 3 is 0.6 and 3 fours are 12, 1.2. So this is a value for x into p. For x square into p, we keep on multiplying this x with this. We are multiplying x with this. We are multiplying x with the third one, and in this manner we'll get the answer. So we will get 0.2 here and 1.2. Then 3 into 1.2 is 3.6. Now we will see 0, 0.2. Then we have a 2.4, and next is 1, 0.8, right? So we will see that these values are already done. So we can find the fourth one also in this manner by multiplying. And when we add it, we'll get the sum of xpx as a 2, which is mu1 dash. This is mu2 dash and mu3 dash and mu4 dash. So we observed all the four raw moments. So what we are going to do is we are going to plug in into the formula which we have discussed earlier, because now we are not going to find a central moment using the tabular form or deviating the mean from each value. What we can do, the first central moment, because they ask four central moment, the first central moment is always 0, so nothing to calculate. The second central moment is mu2 dash minus mu1 dash square. So mu2 dash is 5 and mu1 dash is 2, so we are getting 5 minus 4 is equals to 1. And for the mu3, we will use this formula, and when we plug in the value of mu3, 3 times mu2 dash mu1 dash and plus 2 times mu1 dash cube. So after simplification, you can cross check it on your calculator. It is minus 0.6, and mu4, when we are going to apply the mu4 over this formula, mu4 dash minus 4 times mu3 dash mu1 dash plus 6 times this and minus 3 times mu1 dash 4. And when we plug in all the values and after simplification, we'll get a 2.2. So these are central moments. So we are done with the central moments. See from here, because mu3 is indicating the skewness, so we get an idea that it is a negatively skewed, and mu2 will 2.4, but we want to find out its coefficient with respect to the variance. So when we put in the value of this sigma cube, so sigma is 1, so it is minus 6 negative, so left skewed, right? Mu 3 will also give us an idea, but we want to find out if coefficient of skewness, we can use this formula. And for the coefficient of kurtosis, we are going to use B2, and it is equals to mu 4 upon sigma 4. So mu 2 is 1, and when we, so obviously there is only 2.2 value, and this value is less than 3. So less than 3 means excess value is negative. So negative means it is a left skewed. So we are going to get the name of the distribution is platokurtic. So the first question is done. Now let's see the example for the continuous distribution. Here the PDF for the random variable is given as a 2x and it is valid between 0 to 1, and we want to find out the skewness kurtosis. I will suggest find the coefficient part, right? So let us see what we can do. Obviously we are going to take up the raw moments, first 4 raw moments, ex, and for ex we multiply x with fx. So fx is 2x from 0 to 1. So when we will see, we'll get 2 times 0 to 1 x square, and when we are integrating, we are getting x cube by 3, and limit is from 0 to 1. So when we put the limit of x cube here 1, so we're getting 2 by 3. And in the same manner, when we say mu2 dash, that means ex square. In that case, x square is multiplied with every function in here is working for 0 to 1. So when we simplify it, we get in the function as an x cube. So when you integrate x cube, you are getting x4 by 4 from 0 to 1. Then when you put 1 value, you are getting 1 by 4. So it is 2 by 4, which is equals to 1 by 2. And in the same manner, when we see e x cube, we will get x cube times 2x, then it is x4. So 2 times x 5 by 5 from 0 to 1 will be 2 by 5. And the last one is for fourth raw moment. So we multiply 4, so x4 times the PDF. So it is 2 times 0 to 1 x5. So we will get x to the power 6 upon 6 and 0 to 1. So it is 2 by 6, which is equals to 1 by 3. So in this manner, the raw moment can be calculated. Now raw moment can be calculated. We can write the decimal version also, 0 point, that will be 6, so 0 0.67, this is 0 0.5, this is 0 0.4, and this is 0 0.33. So you can use the decimal or you can use the fractional. In this slide, I have used a fractional part. So mu2, when we substituted 1 by 2 and 2 by 3 square in the formula, we get a 1 by 18. And mu3, when I substituted, you can also cross check the answer. I'll get a minus 1 upon 135. And mu4, when I substituted in this formula, which is a relation with the raw, and we get a plus 1 upon. So from here also I get an idea that mu3 is negative, means it is a negatively skewed. So rate we can also handle with the help of the coefficient. So when we plug in the value, we are getting gamma 1 value. So gamma 1 value we are putting in mu3 upon sigma cube, and when we take a square root of 1 by 18, we get a 1 upon 3 root 2. So this answer is minus 0.566, right? So when you plug in the value of mu3 and sigma cube, so after simplification, it is negatively skewed because negative answer is coming up. And for the kurtosis, when we write down mu4 by sigma 4, because sigma square is given to us a 1 by 18, we can find out the sigma to the power 4. So that will be 18 square, and numerator is a mu4, which is 1 upon 135. So after simplification, we will get 2.4, which is less than 3. So in this question also we are facing the same pattern, which is negative in case of gamma 2. So it is less than 3 because answer is coming out to be 2.4. Or we can say gamma 2 is less than 0, so distribution is the flattened one, right? So flattened one means a platokurtic. So these are the problems. What you can do, if you want to do some more content, so take one example for the discrete and one for the continuous, and find out all the terms. So I hope you got an idea about moment, skewness and kurtosis and how we can implement in the probability distribution, continuous as well as discrete. Thank you.